Just a quick announcement before this next talk. Anyone who's thinking about running a sprint during the sprints, please make sure that your project is up on the wiki on the main PyCon website. And anyone who's thinking about participating in the sprints, which should be everyone because they're brilliant, go on there, look for something that you might want to start or something you might want to join, and sign yourself up. Thanks. And without further ado, we have Mike Baer with the SQLAlchemy Session in depth.
Hey, audio's working? Can you hear me okay? You guys hear me? Okay. I hear it now. Okay. Thank you all for coming, and I got to watch my time. So this is SQLAlchemy Session in depth. We'll try to go a little bit through session, kind of the design philosophy, and kind of a comparison to when you don't have a session. And to talk about that, we start with the concept that the session is designed to work with, which is the transaction, specifically a relational database transaction. So when we work with relational databases, the transaction is the primary system that it uses for managing any kind of data. All the data going in is managed within a transaction, and actually the data that's coming out that you see is usually coming through a transaction as well. It provides a scope around a bunch of operations with just, in general, lots of desirable behaviors, things we like. It follows a model known as the ACID model, and we'll go through what ACID means in a second. And usually, relational databases usually use transactions all the time. If you log into your database and do some insert statements and the data seems to just go in, it's probably using auto-commit, meaning each statement is actually in a transaction. So even if you aren't using transactions, you probably are using transactions anyway. So ACID is an acronym. The first letter A stands for atomic, and most people know this means that the things you do within the transaction are all proceed or fail as a single unit. This diagram tries to show the green box there as a table. And as the time moves towards the right, some rows get added to this table, but then the transaction is rolled back. So what happens is at the end of the operation, the table here, called the address table, is back at the state that it started at. Nothing actually happened because both steps were rolled back as a single unit. And if it committed, then you'd have both rows go in as a single unit as well. So that's atomicity. The next letter, C, is for consistency. Relational databases have a lot of features that are designed to make sure the data that we put in follows certain rules, usually using things like constraints and triggers. When I talk about consistency, I'm usually referring to constraints. The most common constraints are the not null constraint, which makes sure that certain columns can't be empty. The primary key constraint ensures that there's at least one or more columns that define a unique value for every row that's unique, and it identifies that row. And the foreign key constraint makes sure that you have a row referring to a parent row. The foreign key column would refer to the primary key column in a different row. And what consistency does is it affects the order in which we can put data in the database. We might not be able to put a row in the database if it doesn't have all of its not null fields present. And we might not be able to put a row in the database if it doesn't have its parent row that the foreign key refers to present. So it affects the order of operations. Isolation, the I, refers to the fact that things inside the transaction might not be visible to the outside world. And things that happen in the outside world might not be visible to the inside. Historically, this is accomplished using locks. So if one transaction proceeds with several rows being put in, another transaction might be locked and not able to see that information until the first transaction completes. More modern systems use a system called multi-version concurrency control, which means that when a transaction begins, the transaction is assigned a version identifier so that that transaction sees a certain version of the data and another transaction sees a different version of the data, so that both transactions can proceed looking at the same table and even the same rows, but they're able to execute concurrently, seeing different information in the same section. So that's isolation, and it's pretty important to how the session works. And then this is just Borat telling us about durability. Basically means, durability means after you commit and the commit succeeds, you can be pretty well assured that the data has been written to disk safely. So that's the transaction idea. Then we'll talk about how object relational mappers integrate with transactions. So we start with a hypothetical object relational mapper using a pretty straight ahead configurational model. It's not really any ORM in particular. We have a user class and an address class with user and address tables. The user table has an ID primary key column. Address has a user ID foreign key column. Address.user is a many to one. If we had a user.addresses, that would be one to many. And let's say that we're using a system called active record persistence, which means we're going to start seeing what it looks like when we don't have a session. So without a session, we're usually going to have a .save method on our object. So we make a new user object and say .save, and that will emit an insert statement immediately. If we call the .delete method, that'll emit a delete statement immediately. If we modify one of the records and then do .save, that'll emit an update statement immediately. So there's no fancy system here. It's just kind of inserting rows as they go in. The next idea of active record persistence is that there's no explicit transaction present by default. It's using normally auto commit, meaning when you say user.save, the insert goes in, the transaction is committed. You say address.save, the insert goes in, another transaction is committed. If you want to use transactions, the active record ORM provides that feature. You can use some kind of thread local global like transaction.begin, and then you can use several operations within the scope of the transaction and then commit it. So you can do transactions, but they're not on by default. The active record persistence system doesn't assume a transaction is present, so the .save methods don't really have an explicit link to the transaction. There's just kind of this context that happens in the background. The active record persistence model, because we load objects based on their class, like user.get or user.query, there's no central object that's tracking everything we're looking at. So if we load the same row from the same table twice, they're going to be different objects. And we say that those objects are not coordinated on their identity. So user ID number 5, if we load it twice, those will be two separate user objects. If we change some information on one of the user objects, it will not show up on the other user object until we synchronize via pushing the data to the database and pulling it back down again. So that means we're not coordinating on identity. And what happens then? Oh, bullet points. Okay, so to sum up, the means of persistence is provided via the interface of each individual mapped object, object.save or .delete. Objects aren't coordinated on a particular transaction by default. You have auto commit as the default behavior. Objects don't otherwise share any connection to each other. Individual queries for the same row returns a different instance. And a persist operation is always immediate. You say .save, you get an insert update, you say .delete, you get a delete statement immediately in an auto commit or within the transaction that you've declared. So what are some potential, not always, but potential issues with this approach? I think the most obvious is that the way active record tells you to, the way it emits insert, update, delete immediately means that we have to be in charge of the order in which statements are sent to the database. And when I referred to consistency earlier, we talked about the limitation that constraints will make it such that you can't just put a row in if you don't have all the values that are not null. You can't just put a row in if there's a foreign key that refers to a parent row that isn't in there yet. So the way we insert rows to the database, we can't just insert them in arbitrary order. So when we receive the data from wherever we're getting it from, if that order doesn't match the order we're going in the database, we have to manually reorder how we're putting data in the database. It means that our code is going to be kind of polluted by this implementation detail of the order in which rows have to go in. And that can actually be automated. And this code example tries to show kind of the worst case scenario, which is where we just have to track the entire list of things we get and at the end do all the .saves. It's not always, not usually this bad, but the concept of, oh, I have to save this first, then save this, and I can't save this yet, I have to save this, and we have to manually do that is one of the limitations of the active record approach. The lack of identity coordination means that if two different functions are loading a lot of data, and then one of the functions is kind of modifying a lot of those records in memory, the other function, if it's working within the same transaction still won't see the data that the first function put in unless the first function actually pushes the data up to the database. And the other function will then receive the row back via the database. That's because if over here user process 1 loads some user rows and changes some of them, user process 2 loads some user rows, it's not going to, it's a different instance of the user object even though it's the same row in the database. They're not coordinated in memory. So a change to user from number 1 won't be visible on number 2. So if these were coordinated on identity, the changes we make to the user object would be visible everywhere within that transactional scope, and we'll see how that works with the session in a minute. Ambiguous data boundaries mean we don't have a clear pattern when to refetch. So with this one, this means that because there's no explicit transaction, there's not a really nice way to know when we should refresh the attributes on an object. So if we load user ID number 5 somewhere, change some data, and then we do that. And then user number 2 we load somewhere, change some data, it's the same object. If we go back to user number 1, he would have to refresh the .name attribute from the database to get the current data. Otherwise, you see stale data. And we don't want to refresh every time because that would be wasteful. So because we haven't given active record a boundary, hey, here's where I'm done with what I'm doing, we're ready to go back to see what other people have done in the database, it just means it's another thing we have to worry about. And then the most complicated issue, and I hope I get through this slide, is that uncommitted data can leak into other transactions. And what this code is attempting to show, and I don't expect you to follow it, it's just kind of trying to show it. There's a producer and a consumer which could be running in different threads or different processes. The producer is producing a lot of user rows, some of which are loaded from the database, some of which are brand new, in the scope of a long-running transaction. And then it places those user records on a queue. The consumer is then consuming those user objects and then working with them in a different transaction. So there's a mistake in this code, which is that the consumer is treating these rows that aren't actually persistent in the database as if they were. And what can happen is, based on the data, if the data refers to a user row that was inserted but is not actually committed, because of isolation, the consumer will fail because the row isn't actually committed yet, and because transaction isolation means that we usually don't have what are called dirty reads. We usually won't be able to see what a transaction is doing until it's committed. The consumer will sporadically make mistakes and fail to delete the row if it actually wants to delete the row or modify the row, because even though the producer has inserted that row, it's not committed yet. So we're making this kind of silent mistake here that we're not going to see until the data hits a certain pattern that shows that. Does that make any sense at all? Or any kind of, okay, you get it. So there's a mistake being made here, and the active record system is not able to warn us about it at all. Because we're just basically sharing uncommitted data between transactions, and there's no way to know, active record has no indication to know that that's a bad thing to do. So when we use the session, that will hopefully solve all of our issues. Okay, so the session strategy. There's always an explicit transaction present. I mean, now SQLAlchemy has some options for this, but in general, we really want people to have a transaction present at all times, and that's what it does by default. So when the session works, it maintains a cached set of transactional state, which consists of rows with identities, like user row primary key number 5. A row is typically only present in the session if it was either selected from the database with a select statement, or it was inserted into the database within the span of that transaction, which means that all the data that the session considers to be rows in the database came from that local transaction. And when you have an object like the user object or the address object, when it's associated with a session, the object is considered to be a proxy for that row within the transaction only, represented uniquely on its primary key identity. So this is called the identity map, meaning if you have user ID number 5, there's only one of them in that entire session for that particular row identity. And the fact that they're proxies, we'll see what that means in a moment. When we change an object in memory, Nothing really happens immediately as far as the database is concerned, but we accumulate changes as they're created, and then we push them out to the database before we do a query. So we have some data, some new user data, some new address data. We haven't pushed it out, but we want to query the database. So what we do is first we say, okay, let's see what changes are pending, push them up to the database. Now we do our select statement, and then we have the advantage of all the data that we've pushed out to select back again. And at the end of the transaction, before we commit, we do a final push of any remaining pending changes. And this is called the unit of work pattern. So the object as the row proxy. So we use this term persistent. An object is said to be persistent when it acts as a proxy to a row present in the transaction. So this row is normally always known as the result of a select or insert. So the blue box in the middle represents the transaction, which with multi-version concurrency control would have its own version ID, and the view of the address table within that transaction is not necessarily the same as the address table that's physically in the database, because we could have isolated changes that haven't been committed yet. We might have repeatable reads turned on so that we've selected some data. It might have changed on the outside, but we still see what we've seen the first time we selected. These are elements of transaction isolation. So SQLAlchemy only considers the view of data in the transaction to be significant. We actually never really see what's in the database. We just see the view of data as the transaction gives it to us. So over here we have 3 rows, and there's 3 green address objects that refer to those rows as proxy objects. When the transaction goes away, we don't know anything about those address objects anymore. We expire everything about the state of those addresses. And if we ask those address objects for information about their contents, the session that they're associated with will start a new transaction, go back out to the database, and refresh those rows with a brand new transaction. Now we're in a new transaction. An object that's outside of the session that we haven't put in yet is said to be transient. And when we put it in the session and it hasn't been inserted yet, it's said to be pending. So this pending object will become persistent once it's inserted. One more state is called the detached, which means that we had an object which represented a row, and then we expelled it from the session temporarily. And detachment is mostly used for caching and sharing objects between sessions. The unit of work pattern lazily flushes only those rows and columns that have changed, trying to order things as consistently as possible, which minimizes the chance of deadlocks. This diagram is kind of busy. The idea is that the unit of work is this process that pops up as needed, organizes the changes to be made into buckets, which it then sorts in the order of which ones need to go first, which ones need to go second, and then it executes all the statements within that. As it executes statements, it also has to move data between rows. If you have a new primary key, that has to be copied to the foreign key of the dependent object. So it does a lot of work. It does it pretty well, and it's a whole lot of code we don't have to write, thanks to the unit of work. So where did the session come from? It came from this pattern called, the unit of work came from a book written by Martin Fowler called The Patterns of Enterprise Architecture. The Hibernate ORM for Java was largely responsible for the concept of the session. A lot of the ideas in sessions kind of came from this ORM that's pretty famous. It was an influence on SQLAlchemy. The Java persistence architecture is a spec called JSR 220, which kind of grew largely out of Hibernate's model. And finally, SQLAlchemy was really affected a lot by an ORM called the Storm ORM for Python. And as a version 5 of SQLAlchemy, we really made our model a lot more strict due to Storm doing things in a really good way. So Storm's a great ORM. And we're a great ORM too, so we're all great ORMs. Anyway, so we go back to the examples of active record and see how they look in terms of when we have a session. So when we have a lot of records coming from some data files and we need to put them all in, we can worry a lot less, not zero, but we can worry a lot less about the order in which data goes in, because the unit of work is handling most of the work for us. And in particular, it does things like if we emit an update statement, it will make sure that the columns being updated are only the ones that actually changed. If you have a row with a lot of columns and maybe some big large text fields, if your large text field hasn't changed, we're not going to send that whole large text field up to the database a second time. We only change the one little integer value that you modified. And it also will make sure in this example that user objects are inserted first, then the dependent address objects are inserted second, and it'll generally just make sure things are working pretty well. Now, it still can be the case that things don't insert in the right order. If we really loaded a lot of data from somewhere, and there's a lot of dependent data that we haven't put in yet, and then we try to query the database, the auto flush might try to flush the rows prematurely. We still have to get into that a little bit. We still have to say, hey, maybe disable auto flush for this block of code. Maybe we don't put these objects in the session as quickly, but overall, the unit of work is usually going to automate most of the work for us. And if we really need to get into it, we can. But at least we don't have to usually deal with .save, 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 to save this, save that. It's kind of automatic. And also, as we put objects into the session, there's a behavior known as cascading, such that if we have a user object, we put it in the session. If it has 3 addresses attached to it, those all go in automatically by default. You can also configure that. But it's basically automating the work of putting things in the session to a high degree. And it's automating the work of pushing state up to the database in the way that the database expects in order to maintain consistency and not break any of those constraints. The identity map coordinates the state of rows in memory. So our process before, where we had user process 1 loading up a user number 5, and then user process 2 loads up user number 5. We don't have to worry about coordinating the state using the database. If we change the contents of a user of a certain row, the other function that is using the same session will see the same exact change because it's dealing with the same instance of the user object for 5. This works really well with the flush. So we don't have to worry that the flush hasn't actually pushed the data up to the database yet. We know that as user process 2 selects rows, those rows that are already in the cache, the session's row cache, will just pull from the cache and show exactly the state that we've got pending. And identity maps are really popular, and I think people that use them generally agree that they only make life easier. So we have the explicit transaction that provides a nice boundary when data should be refetched from the database by default. This is kind of hard to explain sometimes, but the session model kind of pretends that the transaction is what's known as serializable, which is considered to be the highest level of transaction isolation, meaning that anything you do in a serializable transaction will remain exactly consistent with itself. If you select some rows and select them again, you'll see the same rows exactly the same every time. We usually don't work in serializable isolation, but the session's default model is to assume that any row that you've pulled in the local transaction, we can keep it as it is. We don't have to worry about refetching within the same transaction. At least if you have repeatable reads turned on, you can assume that a row that you've selected will be the same if you select the same row a second time. But if you don't have repeatable reads on, it's still a good default to have. If you really, really want to see what a concurrent transaction has just committed, you can manually expire an object. But in general, the idea that once we load rows from a certain transaction, we don't have to go and fetch it again until we commit the transaction. So once we commit the transaction, then we say, okay, now we don't have a transaction anymore. Other transactions might be proceeding and might be modifying things. So this is all you can all change this. If you don't want it to expire by default, you can do that. But after this transaction ends, it expires all the data. So that if we hit the user 1 object the second time, you will not see stale data. You'll see exactly what the other transaction is committed. And if we work with user 2 down here and then roll back that session, again, that'll expire the state of user 2. And you see, every time we ask an object for its state, we never get stale data, at least at the level of transaction granularity. So that's one, we had to go through some more trouble to have a session in the first place. It's kind of like, oh, what do I have to make this session for? I have to start it, I have to commit it. But it really tells the ORM some nice information about when it can hold on to things and when it can expire things. It's more information that we give to the ORM to work with. And then finally, the implicit transfer of state between transactions is disallowed. This feature has sometimes been a little bit controversial, but I think it's correct that if your producer is pulling up a lot of rows, within a long-running transaction, and then it tries to share that object to some other part of the program that has a different transaction, that's explicitly disallowed. So this code will not work at all, ever. No matter what the data looks like, the consumer will throw an exception immediately when you try to take that user off the queue and put it into a different session without that second session having loaded the row itself to know that that row is in that transaction. So that's a stricter model, but the point is that this code will tell you immediately that it's broken, whereas the active record version won't tell you that it's broken until the data looks a certain way. And that's like the worst kind of error, which is that your code works fine, you put it in production, and then 3 in the morning someone committed some data that actually made it break. So it's better to break sooner than later. That's that. All right. So the last part of this, and I have more time than I thought, which is good, is a live session demo. And I originally thought that this talk would be much more about this live demo. And I spent a lot of time doing what you're going to see. And it's okay, it's kind of interesting to watch. You'll see it. It's an HTML5 graphical, not like an animation that's going to show how the session goes through its steps, so you can kind of see visually what goes on. We start with a model like this. It's, again, the user address model. It's got some columns. It's got the user.addresses as a one-to-many collection of addresses. And then you have this code where we're going to create a user object. We're going to add 3 address objects to the addresses collection. We're going to make a new session. We're going to add the user object to the session. We're going to then commit the session's transaction. And then it'll expire everything. Then we will look at the user1 addresses collection and pull the second element from it and modify the email field to be some new value and then commit that. So we'll see what actually goes on visually. And the way I did this was I used SQLAlchemy events in conjunction with a lot of Python metaprogramming stuff to intercept all kinds of things happening. And then I wrote all of those things happening out to a big JSON file. And then what this HTML thing is going to do is read back the JSON file and replay all the events so you can see what it looks like. All right. So we start, the big blue cylinder is the database. That's the universal symbol for database. The yellow and green boxes are tables, like the so-called physical, not really physical, but user and address table. Those 3 little boxes are connections to the database, and there's like a connection pool down at the bottom in a little SQLAlchemy engine with a connection pool. And there's nothing else going on, so I'll step through this. So the first thing that happens is that yellow box is the user object, and the little beige box inside of it is a little SQLAlchemy thing called the instance state, which kind of tracks things about the object that SQLAlchemy wants to keep track of. So we made a new user, and then we assigned to the name field, and then we said user.addresses. That box there is going to be references to the address object in a collection. And then we made 3 address objects. This is one of them, and then a second one, and then a third one, and then they get appended to the user.addresses collection. So this is really every single thing that happens. And then that red box is the session. We said, session equals new session. And then all those boxes inside are collections that will be worked with as we do things. We add the user object to the session, and it goes, that little yellow box up at the top is the list of pending objects. That will cascade to the 3 green address objects that are related. So it traverses all the collections of user to put related things inside. So now everything is pending. Now the flush begins. And then we haven't talked to the database yet at all. You notice we haven't actually done any SQL or anything yet. We've just worked with objects in memory so far. Now a transaction is established, which is that blue box there. So that basically represents the version. So data is going to be written to that transaction, but not present yet in the actual database because it's isolated. It's going to be on a certain version of the data that's not the version of record yet. So the box represents kind of what our view of the database for the scope of this transaction. What's next? Oh, an insert statement. Great. So as we insert into the user table in the database becomes part of the transactional state. And the yellow row, the yellow line in the middle is a row that we just inserted. The database assigns a new primary key identity for the row and gives it back to us. We assign that primary key identity to the user object, and then we also have to populate that ID field on the foreign key user ID of each of the address objects. So that gets stuck on those objects here. And then after we've inserted the user row, then the address rows can go in. So that's one of them, and that's two of them, and that's three of them. So now all the data is flushed. And then we do some bookkeeping. The objects that were pending now move into the persistent state, where they are being moved from the top to the middle there to the identity map, where they're mapped on their database identity. And then the flush is over, and then the snapshot is committed. You'll see the box just disappeared, and the new rows that we made moved to be part of the permanent storage of the database. This is where Borat goes like that. And now that the transaction is over, we officially don't know anything about the data anymore because anything could have happened at this point. So we expire all the attributes on the user, and that has the effect of the address objects being garbage collected, and they go away. And then the connection goes away back to the connection pool, and that's the end of the first part of operations. And then we say, hey, user, we want to modify user.addresses index number 1. Okay, let me start a new transaction. New connection to the pool, new transaction starts up, load the user row back from the database, make sure it's still there. If it wasn't there, we would throw an object, it would throw an error saying the object has been deleted, because it could have been. We load back the 3 address rows, and then we populate back into address objects, and then we repopulate the collection of address objects on the user. This is all at the beginning of a new transaction. And then we are going to make a modification to the second address object, so it moves to a collection called the dirty collection there. And then we flush it again, and then the row gets, you can't really see it, the row gets modified, and then it moves back to being persistent, snapshot is committed, and then we go back to the state where we garbage collect. And now what this can do, this is just HTML, and I have it up in my blog. You can just kind of, you know, I did this talk in November, and I said it would be good for like a Christmas lights thing, because you can just kind of let it run. And this is what I thought I was going to do. I was going to just have this running in, but I realized I really have to step through each step individually, so you can just go home and put this on and see all the work that a session has to do. And then that is it, and I can show you the fancy that thing. So if we have questions.
I have a question. The auto flush, when does that occur?
The auto flush will occur normally right before you emit a query. So if you tell the session to query for something, it'll flush first, then run the select statement, and then it will flush before you commit the transaction.
Okay, thank you.
Yep.
So I'm using SQLAlchemy for a new project, and I have my model set up with relationships to other models, and they work fine. But what I notice is when I start running load tests with lots of concurrent users, I start getting a lot of detached instance errors on my relationships.
So detachment refers to when the session that the objects were associated. The question was that he's running a lot of concurrent processes, and he's having problems with relationships reporting that they're detached. So what usually happens there is that the objects are lasting longer than the session itself is, and then the object is asked to load some collection like user.addresses. The collection is not there, so it goes out to its session to load that collection, but the session is gone. So what it means is that the way your application is organized, somehow those sessions are disappearing prematurely. Okay. Or alternatively, if you want the objects to work in detached mode, you have to make sure that everything you need to access is loaded ahead of time. But usually I kind of encourage people to figure out why their sessions are going away prematurely. Usually for a web application it's very simple, but for other applications it might not be as simple, so it depends on how things are organized.
Thank you.
Yep.
Howdy, Josh Burkus, Postgres project. Cool. 2 comments, 1 question.
Okay.
Comment number 1 is the C in ACID has nothing to do with constraints.
Okay.
It's consistency as in having a consistent view of the database between different connections, which you've actually implemented, so you should know that. The second comment is, for clarity for users who are using SQLAlchemy with Postgres, Postgres also has something called a session, which has some similarities in concept, but it is different.
I know.
So don't get them mixed up.
Yeah, I've seen that.
Yeah. Yeah, so the third thing is, my question is actually about durability, because it seems like you could have a situation where your code has moved on to the next step, but you're waiting for auto flush, and the application server goes down, and at that point you've actually lost your data.
Well, the auto flush is working within the scope of a transaction, so really it's the commit that you're waiting for.
Okay.
Yeah.
Okay, thanks.
Yeah, okay.
Hi, can you describe the relationship between an instance of a session and the connection pool?
Okay, so when you have a session, you create a new session, and you usually want to give it a reference to a SQLAlchemy engine. And the engine represents kind of a factory for connections. It's a source of connectivity. It's not a connection itself. The engine will have reference inside of it a connection pool. So when the session first is created, it knows about the engine, but it hasn't done anything with the database yet. Once you tell the session to do something that it has to go to remit a select statement or flush, it will then procure a connection from the engine. So it pulls the connection from the connection pool, and then that connection represents the ongoing transaction for what it's going to do. So then it takes that connection and holds onto it persistently until you say rollback or commit. And then when you roll back or commit, the connection is then closed, which has the effect of it moving back to the connection pool and being released back to be used again. So the session is not pulling from the connection pool for every operation. It's pulling from the connection pool per transaction, holding onto it, then releasing it when the transaction ends.
Hey, I'm a total noob to using SQLAlchemy, but I'm trying to understand the trade-offs in terms of performance implications, like having the session object. I was just curious, what do you think the downsides are? Clearly it's worth it, but what are the downsides in terms of performance and so on? Like
so it actually does have a lot of I mean, part of the point of this, oh, you can't see it anymore, there's an animation running, is that it's complicated. The biggest downside of the session is the fact that the identity map needs to know the primary key identity of every object. So what'll happen is you load it, when it persists an object, it has to ask the database, hey, can you tell me what the primary key of that row you just put in is? Because usually when we work, I mean, this is not always the case, but if we're working with integer surrogate primary keys, which is kind of the norm these days, we ask the database to generate those primary keys for us. So, which means the way the Python database API works right now is that you have to insert every row individually and ask for each primary key identity back separately. It means that we can't batch those inserts together. Now, SQLAlchemy these days, if you give it primary key identities ahead of time, it will batch the rows into what's called an execute many. So it'll do that. And then also what causes performance problems is that besides getting the primary key identity, there's a lot of bookkeeping going on. As it loads rows from the tables, it has to figure out where they go in the identity map. It has to see if the object needs to be refreshed or not. There's a lot of rules going on that you wouldn't have in a simple active record system. It's basically, the price you're paying is that there's a lot more automation going on, and it makes your code, in my opinion, easier to write, but the automation comes at a performance cost.
Is that just a limitation of the Python DB API layer, that you can't apply the primary key of a parent object to a dependent object in a creation, or is it something more?
The thing about well, okay, there's two things. Are you asking about the newly generated primary key being available, or the foreign key part of it?
Okay, so when you create your user object with 3 dependent new address objects,
yes,
could you write a SQL statement which created all of those, which got executed in one round trip to the server, or is it?
Right. Well, in my experience, you can execute a statement that will insert multiple rows into one table at a time. If you want to insert into 2 tables at a time, in my knowledge, I would think you'd have to use a stored procedure to do that, to have it in one execution.
You can do it in Postgres, but not in most SQL databases.
Like what, like semicolons separating the statements, or?
With clauses.
Yeah. Yeah, we have to support those soon because people want them. Yeah, right. So SQLAlchemy is working towards kind of the traditional insert, update, delete model. But yeah, that's why I said in my experience, because I knew someone was going to say, oh, no, you can do it. But yeah, I mean, generally, it's partially a limitation of maybe the DB API and the fact that we are trying to some degree target what normal databases normally do. So yeah, it's true you might be able to optimize things for Postgres or SQL Server.
I know there's a new version of SQLAlchemy out recently. Could you give some of the highlights?
Well, the highlights, the most, I mean, from my perspective, it's like what was the most trouble for me to implement. The hardest thing to implement was that we changed how the relationship construct keeps track of what it's doing. We had situations where people had joins between primary and foreign keys where a self-referential table would have a column pointing to itself in a composite. If you go to the site, I have an example of what that means. Basically, be a two-column composite primary key, and one of the columns in the composite foreign key would point to itself. And we had to figure out how to get all the eager loading to work with this column pointing to itself kind of thing. So that was really difficult. And so the relationship mechanics are a lot more clear and solid now. There's a new system for building custom operators, and there's basically if you make a new data type, like we have a new data type for Postgres called the HStore type, and it has all these fancy operators that are specific to the HStore type. You can add new math operations to numeric types. It has a much more extensible typing and operator system, and there's also a system where you can inspect class objects, mapper objects, persistent objects, and get information about them in a very consistent way. We didn't have a good documented system of how to get information about mappings in a consistent way that won't change across releases. So we have that now. It's called the inspector. So those are some 3 bigger features. So I'm going to go home and read about consistency. Because I checked Wikipedia and it kind of talked about constraints, but I guess I didn't get it right. So let's try it again. Well, it was right of everything else. Thanks a lot.